Hi, so let's continue our lecture. This is my video number 4. My video number 4. So in this video, I'll talk on the eigenvalue and eigenfunction. Just give you a introduction or the definition of eigenvalue, eigenfunction. For the solution, we will discuss later. So this week, I'll just give you some introductory remark, some definition, some just to introduce what is the integral equation. So in this video particularly, I'll talk on eigenvalues and eigenfunction, the solution of linear integral equation, how to convert the multiple integral into definite integral, and some special type of integral equation. And at the end, I'll give you some illustrative examples. So first, let's just talk on eigenvalue and eigenfunction. So now we consider the homogeneous freedom integral equation. So homogeneous, we call it homogeneous because look at the fx is 0 there. So this equation has the obvious solution that u equal to 0. So if you put u equal to 0, so left hand side equal to right hand side. So u equal to 0 is the solution of that homogeneous freedom integral equation. So those solution we call it as a zero solution or trivial solution of the equation number 1. So the values of parameter lambda, which the equation, the homogeneous freedom integral equation here, equation number 1, has non-zero solution, which is u is not 0. So we call it the eigenvalue. So which means if we can find a lambda that make the solution is not vanish, make the solution is not 0, then we call that lambda is the eigenvalue. And the corresponding to the eigenvalue, we call it eigenfunction. So we call it eigenfunction, or the solution to that equation, so we call it that eigenfunction. So in other words, if look at this, the spelling error there, you should be u there. So if phi is a continuous function such that phi is different than 0 in the interval ab, and if so, which means phi is the solution to equation 1 corresponding to the eigenvalue lambda naught. So we call that phi as a eigenfunction. So the function phi is known as the eigenfunction of the integral equation 1 corresponding to the eigenvalue lambda, so lambda naught. So this is again, I forgot to put the backslash in the latex. So eigenvalues are also called, this is other names of the eigenvalues, the characteristic values, characteristic number, proper values, or fundamental values. And consequently, for the eigenfunction, we term as the characteristic function or proper function or the fundamental function. So look at the remark down here. So the number lambda is not 0, is equal to 0, is not an eigenvalue, since if lambda is 0, that will give us u equal to 0, which is the trivial solution. So for the trivial solution, we don't have the eigenvalue. So if phi is the eigenfunction of those equation 1, so which means phi is the solution to equation 1 corresponding to the eigenvalue, then c phi, where c is arbitrary constant, is also the an eigenvalue of 1, which correspond to the same eigenvalue lambda. A homogeneous random integral equation of the second kind may generally have no eigenvalues and no eigenfunction. So that is, may not have any real eigenvalues or eigenfunction. It's possible. Next, we look at the Leibniz rule of differentiation under the sign of integration. So let f a function of xy and del f del x be continuous function of x and t, and also let the first derivative of two functions g and h with respect to x be continuous, then the formula given below is known as the Leibniz rule of differentiation under the sign of integration. So if you look at this, so we differentiate with respect to x the integration of fxt with respect to t with the limit g and h. Lower limit is g and upper limit is h, can be written as the right hand side here. Okay, integration of g to h del f del x dt plus f, a function of x, and hx here, dx dt, dh dt minus fx gx dg dx. So this we call it as a Leibniz rule. Then if g is a constant, if g and h are absolute constant, so we differentiate, that give you 0 and that give you 0. So what left is just that. So we have d dx integrate g to h f dt is equal to integration of g to h del f del x dt. So next is the conversion of multiple integral into definite integral. So if you have the multiple integral, so in this case here we have n integral, so all this we have n, this we have n times integration of a function u. It can be written as we integrate from a to b. So look at the limit of integration here, a to x, here this a to x, so x minus t n minus t over n minus t factorial ut dt. So the integral on the left hand side is a multiple integral of order n, while the integral on the right hand side is a definite integral. Now this for the solution of the linear integral equation, so we consider the non-singular linear integral equation, so equation 4.1 and 4.2 here. So where 4.1 is the general Freedom type integral equation, and for the 4.2 this is the general type of the Volterra integral equation of second kind. So the function u satisfying 4.1, 4.2 is called the solution of 4.1, 4.2. So satisfy means that if you substitute u in there, so what we have, the left hand side equal to right hand side. So that's what we call it satisfy. So in other words, a solution of random integral equation for 4.1 and Volterra integral equation 4.2 here is a function u, which means when we substitute into the equation, reduce to an identity. So that we call it solution of linear integral equation. So here is some special type of integral equation. You might heard of you might have heard the this term integral differential equation. So which means in the equation we have the integral sign, we also have the differentiation. So this is the example of integral differential equation. Then we have the integral equation of convolution type. This one we have introduced in the previous chapter. So where we have the kernel is of that form, kx minus t. So this is for the Freedom convolution type integral equation. This is for Volterra convolution type integral equation. Next is the Wiener-Hoff equation. So the Wiener-Hoff equation has the convolution kernel and is defined on the half line 0 to infinity. So we have ux, again the unknown is ux, so k should be k minus t, x minus t here, ut dt fx, where k in the, a in this case is the absolute constant. Then we have a dual integral equation. Dual integral equation for function of one independent variable. Dual integral equation take this form. So we have a pair of equations. So this we call it as a dual integral equation with the convolution kernel. The unknown is still u. You have the unknown appear in both under integral sign as well as outside the integral sign. Then for the singular integral equation, I have mentioned what singular integral equation as well in the in my previous video. So in this case, the definition of the singular integral equation is given as follows. So let gamma be a finite or countable number of simple closed or open arc lying in the complex plane. The one-dimensional singular integral equation has this form. So where does the singular parts come from? Which is that part. Okay. So as we can see here, as zeta equal to t, so the denominator zeros. So that gives you the singular. That gives you the singularity. So where psi and t are complex point on gamma, and at, bt here, at, bt, ft are given function which is known, and u is unknown, k is the Fredholm kernel. So the divergence of that equation is interpreted in the sense of Cauchy principal value, which is defined as that. So this is, we call it as a Cauchy principal value. So we can evaluate this by taking the limit epsilon goes to 0. So what does this mean? It means that in the on the arc gamma, okay, so basically we remove those interval with interval epsilon. Just remove that small parts there, and then we take the epsilon goes to 0. So which means we make it those interval smaller and smaller. Okay, so this is, we call it as a Cauchy principal value. Okay, next I end up with the for this video I will end up with these simple illustrative examples. Just to give you, when we say the solution, what do we mean by the solution of the integral equation? So show that ux equal to 1 is a solution of Fredholm integral equation. This is the Fredholm integral equation. We want to show u equal to 1 is the solution. So what we can do is just substitute u equal to 1 into the equation, into the given equation here, and show that the left hand side equal to the right hand side. So the derivation here is quite complete. So you just follow those things, and it's not difficult anyway. This you can evaluate that part using integration by parts. Then you can solve those expression easily. For the second example, we show that ux equal to 1 plus x squared to the minus 3 over 2 is a solution of the Volterra integral equation, that equation. So ux1 over 1 plus x squared minus integrate 0 to xt ut 1 over 1 plus x squared dt. So this is the Volterra integral equation. So if you substitute this u, the given u here, the solution, into those equation, Volterra integral equation. So from the right side, so just substitute everything there, and then solve that integral, and then use the appropriate substitution. I put it here, t. We use the substitution in this case, t squared equal to s, and then it's end up to 1 plus x squared minus 3 over 2, which is, this is the ux equal to the right hand side. Our right hand side is ux is given here, So therefore right hand side equal to left hand side. So therefore we can state that u equal to 1 plus x squared minus 3 over 2 is the solution to the given Volterra integral equation. Okay, so with those examples, so I end up this video. We stop here. So what we have discussed in this video is that what is the eigenvalue and eigenfunction. How to find the eigenvalue, eigenfunction, that we will discuss later in the more detail in the following weeks. And then the Leibniz rule of the differential equation, conversion of multiple integral equation into definite integral, what is the solution to the integral equation, and as well as some special type of integral equation. So in this subject, not all of this not all of this type of equation will be covered. So we covered particularly on Freedom integral equation as well as a Volterra integral equation. So with that, I thank you. We will meet again in the other video. Thank you.